I'm about to start recording. Does anybody not want to be here? I'm gonna take that as a no. You are all now trapped here. Do not leave.
Are we being paid for this?
Absolutely not. Welcome to another episode of One Take No Mistake. Today, I'm joined by many friends. The most friends I have. It proves that I have many friends. Today I'm joined by my friend Blake, returning guest Sarah, who was here last week, but also newcomers, Chloe, who I play D&D with.
Hello.
And then my good friend Jess, who I also play D&D with and go to school with.
Hola.
So today's gonna work a little bit differently because there's no easy way to explain this. It's a hard topic to explain, and it's kind of torture to people who don't know math, but I want to be real about what I'm learning, and this is one of the things I'm learning, and I've kind of been avoiding it because I haven't been able to understand it, but I had a midterm in the class this week, so...
Help, she's trapped us here!
Yeah, I did do that. You, don't try, they can't see you blink, Sarah. You can't escape.
We're not even being paid.
I pay no one. Capitalism is a scam. Everything's free labor. But that's okay. So, the class that we're going to be going over today is going to be my, transport of biological phenomena class. I think that's what it's called. We just call it transports. It's essentially a applied mathematics course, specifically for the diffusion of chemicals and other substances throughout the human body. If you hated the sound of that, we do too. So you're in good company. Yeah, so like I said before, I had a midterm in this class this week. It went not great by any means, but you know what? I think I got at least a B, so I think I can explain this relatively well. Maybe. We're gonna be dealing with a lot of concepts today.
Maybe.
And a lot of math.
This is very encouraging.
Yeah, math.
Yeah, math! And so, I'm actually not gonna be timing myself today, but I'm also not gonna be requiring my friends to explain it to me at the end. Instead, you can just inundate me with your confused questions, and...
Thank God.
and why I subjected you to this. So, yeah, in an effort to make, biomedical engineering, what I do as transparent as possible, here's something I hate. And love. I love math, but... Okay, so, Blake, you ready?
Yeah, yes,
Okay.
I am ready.
3, 2, 1. Alright. So, so like I said before, transport of systems is about, like, the transport of chemicals through the human body. And we do this using what's called differential equations, which are essentially, your normal algebraic equations, but they have, derivatives in them. Derivatives essentially just meaning rates of things, right? That's all we're saying when we say a derivative. It's a rate of something. So, usually when we talk about problems, we talk about things in steady state, where things are exactly the same, there's no change in its concentration gradient, there's just some amount of material moving through, which is called, flux, right? But once you get to more complicated problems, hold on, give me un momento, por favor.
Already complicated.
It's
Actually, I think I'm being tortured the most as I have taken this course.
this is true. Jess is a biomedical engineer.
I feel like it's torture and triggering.
So, today, what I'm going to be doing is I'm going to be describing I'm going to be deriving a problem for pseudo-steady state. So pseudo-steady state versus steady state is instead of a thing staying exactly the same except for the flux moving through it. Pseudo-steady state, what happens is there's some kind of change in geometry going on, whether that means like you're talking about, in the case that we're going to be talking about today, we're talking about essentially a spherical chemical dissolving into the air, and we're going to find how long the time it takes. We're going to be deriving an equation for time. I'm going to be switching, hold on, I gotta switch this. Okay, cool. Oh yeah, so I'm going to do my best. Here we go. So the equation to describe flux, we start with flux is, we describe flux as NA. And then we, flux is equal to the negative of the concentration, which is what C is. D with the little thing AB, which we'll probably just get rid of AB because it's really annoying to draw that. This D is representative of the diffusion coefficient. Okay, D is the diffusion coefficient, which is essentially how fast something, one material diffuses through another. We have dxa over dr, which this is a derivative, our first derivative. Don't worry, guys, there's gonna be more. This dxa is the mole fraction, and then dr is so that's change in mole fraction over the change in radius. So that's essentially our concentration gradient, essentially, in a way. And then this is our mole fraction of our substance multiplied by another flux. I skipped a little bit to get here. Essentially, and I'm not going to get into this because this is going to be more complicated, we use this thing called Fick's first law of diffusion and the governing differential equation to get to this stage. But just believe me when I tell you that this is the equation we start with. So then we can simplify down to just to solve for NA by subtracting this XaNA from the right side to the left side and then taking out the NA. So we're left with NA times 1 minus XA, whoopsie, is equal to negative CD dXA over dr. And then we divide by this this whole term here because it's in parentheses, and we can do that. And we're left with the solution for flux being CD, so the concentration times the diffusion coefficient divided by 1 minus the mole fraction of the substance times the change in the mole fraction over the change in radius. So this term right here on the end, this change in mole fraction over the change in radius, is talking about our change in geometry. We know that the flux does not stay constant as the radius changes, and so we need to solve for that. So essentially we do what's called a separation of variables. We do a separation of variables, and we're gonna take this dr. I'm gonna do a different color. Oh, nope, that's the same color. Congratulations. And we're gonna move it over here, and then we're gonna integrate it. Because you can take it, if you integrate a derivative, you can get a not derivative. You get the derivative prior. So we get rid of it essentially, right? So we're left with whoopsie doopsie. NA dr is equal to C D over 1 minus XA dXA. And we're going to take each side and we're going to take the integral of it. I'm sorry that my handwriting's really bad.
You're using a mouse to do this, right? You're doing
yes.
very well for using just a mouse.
I'm trying my best. This term right here, NADR, is not a very nice term that we like. We're gonna do this in blue. We don't like this term at all. Like, this is, you can't easily integrate this. You would end up with something that's not useful, because NA is not constant over DR, and we don't know what that relationship between R and the flux is, right? But what instead we can turn it to is we can turn it to a constant. You see, Na, the flux of A, is over like a given point, right? But if we find the total molar flux, which is essentially the molar flux as it relates to the entire surface area, that stays constant over a given length, any radius. So we represent total molar flux with the variable W, which is equal to Na times the surface area, which in this case is 4 pi r squared. There we go. 4 pi r squared, which is very convenient because we have an Na in there. So what we can do is we can multiply this by essentially 1, but we're gonna define 1 in this case as 4 pi r squared over 4 pi r squared, which is in fact 1. And so what we're gonna do is we're gonna take this and we're gonna put it back into our equation. And so we get we're gonna multiply it, so we're gonna get Na. Is there a copy button?
Yes, but
I made a discovery. And then we're gonna lasso this. It's gonna be a very bad integral, but it's gonna be fine. Oh! Okay, here we go. So, when we do that, we can then say that this Na 4 pi r squared is now equal to Wa. So we get Wa over 4 pi r squared dr. I'm not even gonna bring this down, not yet. And then the integral. And then what we can do is Wa is a constant, so is 4, and so is pi. All these are just numbers. And in an integral, one of the properties of it is we can just drag those out of the integral. So we can then simplify this integral even farther by doing Wa over 4 pi is the coefficient to this integral dr over r squared, which is a much, much simpler integral than what we started with. So if we integrate, so now we can integrate this side and we can integrate this side because the C and D are both constants as well, so those can just get pulled out. And 1 over 1 minus xa is not a hard integral either. So when we do all that and we take the integrals of this, I'm just gonna skip a few steps, skip the integral steps, no one cares. We get Wa, the total molar flux, right, is equivalent to 4 pi C, the concentration, times the diffusion coefficient, times the radius, times another coefficient, but we put it at the end because it's a longer coefficient. It's not quite a coefficient, but pretty much it's a coefficient. 1 over 1 minus x of a, or xa, right? We're going back to total molar flux because there's more definitions of total molar flux. Sorry, I'm looking at the video right now, and Sarah's face just looks like the most in-pain face I've ever seen in my entire life. I've never seen such torture in someone's face as I'm explaining math to them. So, this W, total molar flux, is also equal to the density, which is what this weird P is, over the molecular weight, times the change in volume over the change in time. So essentially we're saying the molecular weight of it, or the density over the molecular weight, which are both constants, mostly, give or take, multiplied by the change in volume of this thing is equal to the total molar flux, which also, once again, makes sense if we think about that total molar flux is also equal to the flux across the surface times its surface area, so the change in volume thing kind of makes sense. But we can simplify this down even further into a more reasonable term for this problem, this dV/dt term. And we can say that W is equal to 4 pi r squared times the density over the molecular weight times the change in radius over the change in time. So instead of making it volume-based, we make it radius-based, which is, you know, what our problem is in. So this is a really bad 2. I apologize for that. So we can take this whole equation, and we can set it equal to the W that we just found. So we can say that this WA is equal to, and from there we can just simplify. So in this case, this 4 pi, I'll do it in red, this entire 4 pi term cancels out, because if you divide by 4 pi on either sides, both of them cancel. This r term goes away, and then this becomes just, instead of r squared, it just becomes r. And so we're just left with the concentration, the diffusivity, this natural log term, r, the density, the molecular weight. Everything I've said so far is a constant, pretty much a constant, except for r. And then this dr/dt term. So remember before when we separated out the dxa and the dr on two sides and integrated? Well, we're gonna do that again. Oh god, I've broken Jess now too. Oh no.
I stopped listening.
Good. Okay, you've been through enough pain.
I was going, who hurt you?
This class hurt me. So if we put it back into the thing again, and we're gonna bring this dt over on this side, we're gonna give it a little space because we're gonna add an integral later. And then we rewrite this term. So like I said before, the rho and the molecular weight are both constants, as is that negative. So you pull out the negative, you pull out the rho, you pull out the m, and then you're just left with r dr. And then we can integrate both sides. And this integral, both of these integrals are a lot nicer. The integral of dt is just t. And then the integral of r dr is just r squared. It's r, yeah, it is r squared over 2. You're right. I'm sorry. No, I forgot to introduce boundary conditions. It's fine. No one cares. Essentially what we're also going to say here is these are not going to be indefinite integrals.
Okay.
I feel bad. I explained this poorly.
This way, we do not record on Friday nights.
This is why I record on Friday nights. So essentially what we're gonna say is instead of just taking the random integral of t or the random integral of r dr, we're gonna say that this thing has some initial conditions, which we call boundary conditions, where we're gonna say that at time is equal to 0, it's gonna be some initial r is gonna equal some initial radius ri. And then we're going to say when time is equal to t, any given time t, we're going to say r is equal to rf, standing for r final. Alright? And before there was actually supposed to be some boundary conditions here. They're just a lot harder to explain, so I'm just going to ignore them. For now.
My real math works.
Look, there's a lot you guys are missing. Okay, so we take the integral of this, and we plug in these initial conditions, and what we get is we get c d. Hold on, I'm just gonna. So the derivative, like I said before, the integral of this is just going to be t, and then the integral of this guy is going to be ri squared minus RF squared all over 2. And we can rearrange this however we want for whatever variable we want. But for my class, we arranged it to solve for time, so that's what we're gonna do here. And all of this stuff is constant, so we're just gonna take this and we're gonna say t is gonna be equal to, and there you go. That's the whole derivation. What's my time, Blake?
19 minutes and 57 seconds.
You failed.
I was not expecting to derive this in 5 minutes. And I think most of it is just me very slowly writing.
Are you doing this on a mouse pad? Or like using your mouse?
Absolutely. You can't see it, but I'm holding up my mouse right now. This is pain. This was pain right here to write this out via mouse.
Honestly, I was gonna give you a 3 out of 10. I'm gonna upgrade it to a 6, knowing you did that on a mouse.
Thank you.
Yeah,
Fuck, you still can't see it. I got, actually this is better. This is the derivation I had to do for my midterm, which I derived the day before as to show my friends how it worked, unintentionally. My handwriting's a lot neater when I'm not using a mouse pad, and a lot more readable. So, though holding it up to a camera doesn't make it look particularly great. But that's everything. Do you guys have any questions?
Isn't it final minus initial, not initial minus final for the integration?
It's top minus bottom, right?
Yeah.
Yeah.
So it should be like RF squared minus RI squared, not RI squared minus RF squared.
Look,
right?
I copied this from my teacher's PowerPoint presentation. So take it up with Dr. Rodell.
What a man.
Hold on, I'll double check to make sure that I didn't copy that incorrectly, which I have been known to do before. If I get...
Oh, my comments! My microphone wasn't working.
Oh no.
Re-record. Time to do it again. Round 2.
Round 2,
I was
guys.
just gonna say, Hannah, that you have, you've not disproved my math is the square root of all evil comment.
I'm have the PowerPoint up right now. I'm sharing it,
I can see it.
yeah, it says RI minus RF. Dr. Rodell could be wrong.
It makes no more sense when you can read it.
You know what it
Oh,
is?
wait, no, it's the negative. It's the negative. Yeah.
Negative. Yeah,
I
I was about to say, if it was top minus bottom, then shouldn't
Why
your
can't I
team
erase
be
it?
negative?
This man is notorious for switching signs and not telling you how he switched signs. So.
Why won't it let me? I don't know
It
if you
won't
guys...
let you erase. Yeah, I can see. It's not letting you erase.
I don't...
Spirit, did you save it?
I don't know.
Maybe you need to go to the
Ah!
erase.
Ah!
Oh.
Ah!
Oh yeah.
Alright, that's enough. This is a half-hour long recording of me torturing my friends.
It'll take 8 years to upload.
It'll only take a billion years to upload.
So
Alright, everybody say
You
goodbye.
know what? Final thoughts. I sort of understood what was happening.
Yeah,
Yes!
same. I was
I
gonna say, like,
understood why you were doing things.
Yeah.
And I understood what most of the letters meant. I feel learned. I feel smart.
That's the goal. That's all. You know what? I've accomplished my goal. I've done what I needed to do here. Alright, we gotta go. Discord link in the description below. Subscribe, like, comment. You should guys, I think the YouTube algorithm is all about commenting. I'm convinced. This is why my first video has like 650 views, because it has a bunch of comments. So like, just comment away. Have a good one. I'm sorry for your brains.
No, you're not.
No, I'm not. Have a nice
That was
day,
just
guys.
easier.